Hello dear students, today I will discuss about Bayes theorem. That is a probability chapter, Bayes theorem. Just in the previous class we have seen that the conditional probability, multiplication rule of probability, independent events, etc. Okay, so Bayes theorem which depends on conditional probability. Here just what is the main requirement for Bayes theorem? Just I want to discuss about that. Suppose, because we know about additional rule of probability, multiplication rule of probability, and independent events, mutually exclusive events, and all the formulas. Okay, just here Bayes theorem is required for finding reverse probability. What is reverse probability? Just consider bag 1. This is bag 1, okay, and this is bag 2. Suppose we are having two bag. Okay, first 2 white and 3 red ball. Similarly, suppose 4 white, 5 red balls. That means, for understanding what is the reverse probability. Reverse probability means, just suppose we have one bag, two bags are there, bag 1 and bag 2. Okay? And first bag contains this 2 white balls, 3 red balls. And second bag contains 4 white balls and 5 red balls. Clear? Now, we are having two bags. Just now draw one of the ball from one of the bag. Just draw a ball from one of the bag. The situation is what? Just we have to draw a ball from one of the bag. One of the bag means there is what situation? Just first take first bag and then draw a ball, or first take second bag and draw a ball. This is the situation. And probability of drawing red ball. But drawing red ball, just first of all we have to draw either first bag or second bag. That means just first draw a bag, select a bag and then draw a ball and find the probability. That is very simple. Out of two bag, selecting of one bag is 1 by 2 bag total, so 1 by 2 probability, selecting any of the bag. And then we have to select red ball, drawing red ball. Here red ball 3 by 5, here red ball 5 by 9. Just you can find the probability. But if drawing red ball, just it is given that ball comes red, so what is the probability? The red ball comes from the second bag. That is first, in the first situation, just we draw the ball after selecting bag. Select first bag and then draw a red ball. Select second bag and draw a red ball. But here, drawing ball is red. And what is the probability that this red ball comes from second bag or comes from first bag? This is reverse probability. So this reverse probability can be found by using conditional probability, and Bayes introduce a formula just for finding reverse probability of an event. Okay. So for Bayes theorem, that is for finding reverse probability, just we require two concepts. First, we know whenever an experiment is there, the sum of the outcomes of an experiment is always there, and sample space is what? Collection of all the outcomes. Sample space contains all the elementary events, that is all the outcomes. By combining 2-3 outcomes may be an event, or single outcome is an event, that is elementary events. Okay. So here, suppose we are having sample space of an experiment. Yes, what? Sample space. Okay. And because whenever an experiment is observation is done, then we are having some outcomes, and outcomes are in the sample space. And here total probability theorem is required for deriving the formula of Bayes theorem. Okay. So first of all, just we want to understand what partition of a sample space. Partition of a sample space. Partition of a sample space. We know sample space contains all the elementary events, and this is a set, all the elementary events. Now, just we divide partition of sample space means just if we have some subsets of this, that is some events, that is suppose E1, E2 up to En events. Suppose n events are there. All the events are subset of this sample space. Clear? If these events are non-empty, because events what? Subset. So non-empty subset. That is having probability sum of all the events having probability non-zero probability. And pair-wise disjoint. Pair-wise disjoint means just by taking 2 and intersection is not 5. Sorry, 5. Intersection is 5. Pair-wise disjoint means not join. If events these such that E1 intersection E2 and E2 intersection E3, E3 intersection En and etc. that is pairwise I, we can use Ij is equals to phi. I equals to j equals to what? 1, 2, 3 and so on up to n. Okay, this, and here I equal to not j. I equals not j equals. Here Ij, we can write Ij is this and I is not equals to j. I is not equals to j and Ij both are having value 1 to n. Means any two, take any two and find out intersection will be fine. Pairwise disjoint. This is what? Pairwise disjoint. Pairwise disjoint. Pairwise disjoint. And also what? Non-empty. Non-empty pairwise disjoint. And all are subset of this. All are subset of S. And disjoint, pairwise disjoint. If taking intersection of any of two, then you can get phi. This is first, this is second, this is third. Third is what? Third is exhaustive. Exhaustive. That is E1 union, E2 union, E3 union up to union En equals to S. Means union of all these gives sample space. All the events, we know events are what? Subset of sample space. For a random experiment, S is sample space. For a random experiment, S is sample space. Sample space means what? Collection of outcomes. Collection of outcomes. That is sample point. Well, points. Sample points, collection of outcomes, these are these. Elementary events or elementary events. Elementary events. Sample points, elementary events. And subsets of this S is an event. And suppose E1, E2, E3, En are subset of this sample space, N events, such that they are non-empty. That is having probability non-zero probability. Non-empty means non-zero probability. And such that pairwise disjoint, that is taking intersection of any two, you can get phi. Pairwise disjoint. And also exhaustive, that means union of all these events gives S. If these three conditions are satisfied, if these three conditions are satisfied, if this, then event E1, E2, E3 up to En is called a partition of sample space. S. So this is the partition. So what is partition of a sample space? Just I think it is clear now. because for any experiment, for any observations, we can get some outcomes, the collection of outcomes keep in a set that is called sample space, and any subset of all the elements are called sample point or elementary events, and any subset of this S is events. So if n events just like this or a subset of this such that pairwise disjoint exhaustive, then we say that these events constitute a partition of sample space. Clear? Exhaustive also. So this is partition of the sample space. Now we will discuss about theorem of total probability, because for Bayes theorem of total probability theorem is main thing. Okay. So definition of total probability theorem and formula for total probability theorem is very simple by using this partition. Main thing is just remember this partition. What is partition? Because in any experiment we will get some events that will constitute a partition of sample space. So we can use total probability theorem also, Bayes theorem. So this is partition. Okay. Now just theorem of total probability. That is total probability theorem. Okay. So total probability, for defining total probability theorem, just we require a partition. Okay. Just write, take a partition of sample space corresponding to some experiment, random experiment, and then we can define probability of any event in terms of conditional probability. Okay, here total probability theorem. Total probability theorem. A theorem on total probability. Okay. So just for this statement, very simple statement. What? Let statement just we take yes partition of sample space. Let E1, E2, En be a partition of sample space S associated with a random experiment. Partition means, all are non-empty, having non-zero probability, pairwise disjoints, exhaustive. Then the probability of any event associated with S is given by probability of any event associated with S this sample space is given by PA is equals to E1 A by E1 plus E2 A by E2 En probability of A by En. Clear? Okay, this is total probability theorem. So very simple. What? Suppose we are doing some experiment, then corresponding sample space is S, then take its partition, any partition. Partition may be differ. Partition is not unique. Maybe different type of partitions for a sample space. There may be many partitions. Okay, so take any partitions of the sample space. And sample space partition means what? You know, all the events you want to n are having non-zero probability. That means non-empty, pairwise disjoint, and exhaustive. That means union of total is equals to S. Then suppose any event related to sample space S. Event means what? Subset of sample space. So for any event associated with S is given by this formula. Here condition of probability is this. What is this? PA by E1 means probability of event A. E1 already occurred. So just PE1, that's probability is this, into happening A, provided E already happened. This. Similarly for second, for third, for nth. So this is total probability theorem. It can be also written like this. PA equals to, in short, in summation notation, I equals to 1 to 10 P E I upon into E A by E I. Okay, this is total probability theorem. Clear? So note down this, because this total probability theorem is used in deriving the formula for Bayes theorem. This is main part. Okay. For total probability, its proof is very simple. Very simple. Okay. So just proof is not required. Just remember this formula for total probability theorem. Okay. Where U1, U2, U3, En are what? A partitions of sample space. Okay. Now, Bayes theorem. Just I will give formula for Bayes theorem. Bayes theorem gives reverse probability. Okay, so Bayes theorem Bayes theorem. Okay, so here also we take a partition. Okay, this statement you can write, because the statement is very important for understanding also, because by using this theorem we will solve all the questions of next exercise. Okay, So where statement, what is a statement? If E1, E2, En, B are n events, if these are n events which constitute a partition of the sample space S. Partition means what? That is, we can write what? E1, E2, En are pairwise disjoint exhaustive E1 union E2 En equals to S. Pairwise disjoint means what? Just you can write pairwise disjoint means are pairwise disjoint EI intersection EJ is equals to phi, I is not equals to J, I and J is equals to 1, 2 up to n. Pairwise disjoint having non-zero probability, that is what? All I's are non-empty, and E1 union E2 union and so on En is equals to S. That is exhaustive. Then just we write about partition. E1, E2 of En are what? Partition. N events, non-empty events, non-zero probability, pairwise disjoints, exhaustive. Then the probability of then for any event A with non-zero probability. Then for any event A with non-zero probability, P EI upon A is equals to, this is reverse probability, because E1, E2, E3, En are previous thing, hypothesis. We can see here in the case of Bayes theorem, just EI's are known as hypothesis. PI, probability. So probability of this priori probability, okay, called what? Priori probability. Hypothesis is called E1, E2, E3, En. EI's are hypothesis. So priori probability means PI, just this PI, PEI, and PEI by A, PEI by A, EI by A. Posteriori probabilities. This is priori probabilities. This is priori probability. This priori probability, okay, and this is posteriori probability. This is some special notation for a special name. Priori probability, that is PEI. PEI, EIR, E1, 2, 3 up to EN. They are called hypothesis for in case of Bayes theorem. And its probability PI, priori probability. And PEI by A, when A is any event of non-zero probability having already happened, and then the finding the probability condition, this conditional probability is known as posteriori probability. This, okay. So here in this theorem, the result is what? PEI by A equals to PEI into P A by EI upon sum of P EI Z P A by Z. Here Z equals to 1 to n and I equals to 1, 2, 3, n. This is Bayes theorem. PEI by A is equals to PEI into PA by EI. Here I equals to 1 to 3 means 1, then here 1. But here the same type of thing, but here j equals to 1 to n, j. Means this is total probability. This is. So this is the formula. Posteriori probability of the hypothesis EI. Posteriori probability. This is priori probability. So this is main formula for of Bayes theorem. It can be proved very simply. Okay. So related to Bayes theorem, this is our notation and formula is this. Just remember it always, because this is the main formula. By using that, we have to find solution of important questions. Just next exercise. Okay, this is Bayes theorem. Its proof is very simple. By using conditional probability, we can find this result. So see how. Just use conditional probability. Here we know E1 to E3, En are what? Partitions. So just proof is very simple. How? Just see. Proof. By using what? Conditional probability. By using conditional probability formula. What is conditional probability formula? Just we require what? PEI by A. P EI is an event, A is also an event. So conditional probability, what? P EI intersection A upon PA, I equals to 1, 2, 3, N. Conditional probabilities. PE by A equals to PE intersection A by P. Okay. And again use multiplication rule. Multiplication rule. This P EI into P EI by A. Using multiplication rule of probability. Just this. And here PA. Now use total probability theorem. Total probability theorem for the same partition. PA equals to what? Here PEI into PEI by A. Here I equals to 1, 2 up to N. PA equals to sum of P is J up into P A by J. J equals to 1 to N. Using total probability theorem. Total probability theorem. So P EI by A is equals to this. So this is our formula. Conditional probability, multiplication rule, and total probability theorem. Just using these three, we can get this. What is this? Posteriori probability of hypothesis E This is EI is called what? Hypothesis. Hypothesis. The posterior probability of hypothesis. Posterior probability. It is given by this. And priori probability means only this. In case of Bayes theorem, just EI known as hypothesis. Okay. So this is the formula of Bayes theorem. Clear? So just we have to use this formula for solving questions. Okay. So take question from exercise 13.3. So there are total probability theorem and Bayes theorem. Just see the question first. Okay. The question first is an urn contains 5 red balls and 5 black balls. Okay. So just because for finding probability of an event for any questions, just you have to understand the questions well first and then you can find. Here the question is given just like an urn contains 5 red, 5 black balls. Okay. And here a ball is drawn at random, its color is noted and it's returned to the urn. Moreover, 2 additional balls on the color drawn are put in the urn and then a ball is drawn at random. What is the probability that the second ball is red? So what is the process here in the questions? Just in this question solution, here an urn contain 5 red ball and 5 black ball. Okay, an urn contain 5 red ball, 5 black ball. A ball is drawn and note its color. Okay, and again put the ball in the urn. And also just of that color 2 additional ball added to this ball in the urn and drawn a ball, finally drawn a second ball. This is our experiment. Okay, and find the probability. What is the probability that second ball drawn is red? Okay, first of all, very simple. In first case, just draw a ball, then drawing red ball. Probability, what will be the probability? 5 by 10. 5 by 10. Drawn ball red. And second time, just additional to red ball, add to the urn. That is 7 ball will be there. 7 ball will be red after putting additional 2 ball. So in that case, second ball drawn and for getting red ball, probability will be what? 7 by 12. This is 1 by 2, 7 by 12. This is first process. If first ball is getting red. If first ball is getting black in first, in second. If first ball black, we have to find the probability of getting red ball in second. So here red ball, second row, red ball, red is second by doing this, and black in first, 5 by 10, 1 by 2. And in this case, just 2 black ball also added this here. So 7 black ball is there. In second case, getting red in second. What? 12 by 5 by 12. Because 5 is red, ball are red, 7 are black. So this. Maybe this situation, maybe this situation. That is this and this are plus. Either this or this. Both are together. First this, then this. So this into this. That is 1 by 2 into 5 by 12 plus 1 by 2 into 7 by 12. Okay? 1 by 2 into 7 by 12 plus 1 by 2 into 5 by 12. So this is the required probability. That is here, what is used? Total probability theorem is used. Okay, so for writing, how can you write this in details? The solution of this question, just you can write in short just like this. Question 1. Urn contains 5 red, 5 black balls. Okay? Let in the first draw, red ball is drawn. Or you can write if in first draw, drawn ball is red, then in first draw, just draw. If first drawn ball is red, then probability of red ball in first draw is equals to red 5 by 10. 5 by 10 equals to 1 by 2. Because in first draw red ball is drawn, so just put the ball in urn and also additional to red ball added to the additional according to question, add to red ball in red ball to urn. Then probability, then number of red ball will be 7 in R. So, probability of getting, because in the second row just we want red ball, so probability of getting red ball in second row, we will consider red ball in second row. So red ball in second row is equals to what? 7 by 12. 7 by 12. Because red ball 7. Also, if just same process, if first drawn ball is black, then red ball in second row, what will? If first drawn ball, just you write, first drawn ball is black, then probability black ball in first draw is equals to, in first draw black ball 5 by 10, because 1 by 2 is very clear, because 5 black balls, so 5 by total. According to question, to add to black ball, because noted the color, so add 2 black balls to the R. Then number of black ball will be 7 in R. So probability of, in the second time, just we have to consider only drawing red ball. So probability of red ball in second draw. Red ball. So red 5. So 5 upon 12. Because black is 7. So 5 by 12. Okay? 5 by 12. Thus, this two situation may be, thus the probability of drawing second ball, thus the probability of drawing second ball as red is what? This situation and this situation, both will be plus. So this situation means what? 1 by 2 into 7 by 2. 1 by 2 into 7 by 12 plus this situation. 1 by 2 into 5 by 12. So 1 by 2 into 7 by 12 plus 1 by 2 into 5 by 12. Just you can solve it. Finally, after solving this, just 12 by 24, 1 by 2. So 1 by 2. So this is answer, 1 by 2. Okay. So this, in this theorem, Just we use what? Total probability theorem. So just understand the questions first and then try to find the probability of required event. Okay. This is was the first questions. Just write the statements of our, first of all, just detail what is partition and then total probability theorem, the statement, and prove also. You can see in book. And also base theorem, what is the statement, how can you prove it, and solve questions from examples in your math copy and send me solution of 2-3 questions for your attendance. Okay. Just in the next class, I will discuss about questions one by one from exercise 13.3 from question second to onwards. Okay.